name is Dr. Esther Trufan, and in this video, we are going to talk about the polarity of molecules. The polarity of molecules depends on two considerations. First, it is going to be the bond polarity. If we have at least one polar bond in the structure of a molecule, the molecule could be polar, but it's not necessary that it is. And the second consideration is symmetry. If the arrangement of the polar bond is symmetrical, then the symmetry will cancel out polarity. However, if the arrangement of the polar bonds is unsymmetrical, then we will likely have a polar molecule. Let's look at a couple unique examples. Here we have water, where we have hydrogen and oxygen. The first requirement is to determine whether we have a polar bond or not. So we calculate the electronegativity difference between the two connected atoms. Oxygen has an electronegativity value of 3.5 and hydrogen has an electronegativity value of 2.1, giving us a difference of 1.4. This confirms that the hydrogen-oxygen bond is polar. Now we have two of these bonds, and if we draw the Lewis structure for water, we have this arrangement with the oxygen connected to the two hydrogens through single bonds, and the oxygen also has two lone pairs on it. There are a couple ways to look at the symmetry of it. One way is to look at the different geometries. So the electron domain geometry here is tetrahedral. The molecular geometry is bent. And because the two geometries are different, you could say that the geometry is unsymmetrical, giving you a polar compound. The other way to approach it, and this is commonly found elsewhere, is using the electronegativity values and how the electronegativity influences the direction of the electron transfer. So hydrogen will donate electron density to the oxygen on the both sides. So the electron density is moving towards the oxygen. It's moving in one direction. It isn't canceled out, making the arrangement unsymmetrical. And so that causes the molecule to be polar. And we know from experience that water is a polar solvent. Another example is formaldehyde. It contains carbon, hydrogen, and oxygen. And we can determine the electronegativity values here. The electronegativity difference between carbon and hydrogen is 0.4. It's 2.5 minus 2.1, giving us 0.4, making those two bonds nonpolar. And then we look at the electronegativity difference between carbon and oxygen. It is 1.0, making the carbon-oxygen bond polar. So we have at least one polar bond, making this potentially polar. Next, we look at the Lewis structure. And here we have carbon attached to the two hydrogens via a single bond and to the oxygen via a double bond. Now, in this case, the two geometries are exactly the same. Both are trigonal planar. However, one bond is different from the other two. If we look at the electron density transfers, the electron density moves from hydrogen to carbon and then from carbon to the oxygen. So the electron density is moving in one direction, making our molecule polar. Another way to look at it, this is not a completely symmetric molecule because on the one side we have oxygen and the other side we have two hydrogens, giving us an unsymmetrical arrangement. This is methylene difluoride or difluoromethane. It has two carbon-hydrogen bonds, which we already know are nonpolar, and two carbon-fluorine bonds, which are very likely to be polar, but just to make sure, let's calculate the electronegativity difference between carbon and fluorine. It is 4.0 minus 2.5, giving us 1.5. At 1.5, this is a very, very polar bond. Then we look at carbon, and there are four things around it, the two geometries being identical. However, the four bonds are not exactly the same. So the two hydrogens are pushing electron density towards carbon, and the two fluorines are removing electron density from the carbon, making this an unsymmetrical arrangement and giving us an overall polar molecule. For nonpolar molecules, we need to negate everything that is associated with polarity. The first thing is not having a polar bond. And we already know from our previous calculations that the electronegativity difference between carbon and hydrogen is 2.5 minus 2.1, giving us 0.4, making this a nonpolar bond. If the only type of bond inside the molecule is nonpolar, then the molecule itself is nonpolar. Another way to get to a nonpolar molecule is to have polar bonds in a fully symmetric arrangement. So here we have carbon and fluorine, and we already know that this is going to be a polar bond. The electronegativity of fluorine is 4.0. The electronegativity of carbon is 2.5, giving us an overall electronegativity difference of 1.5, making this a very polar bond. However, we have 4 fluorines surrounding the carbon, and that means that each fluorine is going to draw electronegativity towards itself from the carbon, and because they are all fluorines, they're going to pull with the exact same intensity, canceling out the polarity of this molecule. So we do have a polar bond, but we have a symmetrical arrangement of those polar bonds, making our molecule overall nonpolar. There are some other considerations here. If we are in the chemistry laboratory, we can easily test whether a molecule is polar or not simply by seeing the way it interacts with polar solvents. If it is soluble in polar solvents or miscible with polar solvents, then it is going to be polar because our definition is like dissolves like. Another consideration, especially for the organic chemistry lab, is the testing with a nonpolar solvent. In general chemistry, this likely involves oil, but in organic chemistry, it could involve hexane or other kinds of nonpolar solvents. If your substance is soluble or miscible with these nonpolar solvents, then you can consider it nonpolar as well. And then the final consideration is the dielectric constant. This is the interaction of a substance with a solvent. A dielectric constant is a numerical value that you can find in various tables. Materials with similar dielectric constant values are going to be mixed readily with each other. So let's look at one not so clear example. Here we have a fatty acid, and in all fatty acids, we have a very long hydrocarbon chain, which only contains carbon-carbon, which are pure covalent, and carbon-hydrogen, which are nonpolar bonds. However, at the end of it, we have a carbon-oxygen double bond and a carbon-oxygen single bond and an oxygen-hydrogen single bond, making this contain a substantial number, in this case 3, very polar bonds. However, when we look up the other considerations, if we mix oil with a polar substance, then it is not going to dissolve in it or not going to mix with it. Think water and oil are not miscible. If we take oil and combine it with a nonpolar substance like hexane, it will easily dissolve in it or easily mix with it. And then finally, looking up the dielectric constant value. The dielectric constant of a fatty acid is very close to 0, making this substance overall a nonpolar molecule instead of a mix of polar and nonpolar. The nonpolar in this case wins out. However, if we have a lot of the polar groups, that may change the equation and it can turn an otherwise organic compound substantially more polar.